Lesson 3.1 Exponential Functions. Exponential functions are modeled by y equals ab to the x, and they're called exponential because x is the exponent. So x is in the exponent. That makes it exponential. A is the initial amount, which is also the y-intercept, and b is the base. X is our exponent. If your base is greater than 1, you have exponential growth. Notice our shape, it's almost level on the left, almost constant, and then it starts getting bigger, and then it starts getting bigger really fast. That's exponential growth. Exponential decay is when the base is between 0 and 1, and it's just reflected over the y-axis. It starts by steeply going down and then levels out. You can plug in any number, any real number, for the exponent. Notice the graph goes all the way from the left, and it keeps going towards the right, so the domain is all real numbers. However, the range is above 0. So from 0 to infinity, and it actually does not include 0. There is an asymptote, and like the asymptote from rational functions, this asymptote just shows what's going to happen on one side of the function. In this case, with exponential growth, on the left side, it's going to level out to the line. And our y-intercept is 0, 1. We can apply transformations to exponential functions. Put the a, the h, and the k in there. Remember, a is a vertical stretch, and if a is negative, it's reflected over the x-axis, so it's upside down. H is how far it moves to the right, and k is how far it moves up. Well, with the transformations, the domain is still all real numbers, but the range has changed. It was 0 through infinity, but if we're going to go up or down, that's k. So it's k through infinity if a is positive. If a is negative, it's upside down. So it'd be negative infinity through k. Our horizontal asymptote was y equals 0. But again, we're going to go up and down k, so it's now y equals k. And the y-intercept would be 0a plus k, but only if h is 0. If h is not 0, then the y-intercept is just something different. To graph exponential functions, just make a table. So let's graph 4 raised to the negative x plus 3. All right, so it's going to be stretched. Well, our base is 4. Our a is 1, so it's not stretched. But we are shifting up. And we have this negative. A negative exponent means that we reciprocal the base. So since the base is now between 0 and 1, this means it'll be decay. All right, so a table of useful numbers. So negative 2 is 19, negative 1 is 7, 0 is 4, 1 is 3.25, 2 is 3.06, 3 is 3.02, 4 is 3.00. 5 is 3.00. Those are not the same because there's more decimal places. And 6 is also 3.00. But again, those are not the same because there's more decimal places. So plot those points. Negative 219 is way, way, way up there. So we're going up. We have negative 17 is actually there. 0, 4. 1 and 3.25, 3.06, 3.02, 3, 3, and 3. We had our horizontal asymptote was y equals k. Here k is 3, so we should have an asymptote at y equals 3. So let's go ahead and put that on our graph, and notice our graph goes down towards it. So it comes down, curves, and goes right along that asymptote. Exponential functions are what are called one-to-one, which means each x gives a unique y. To be a function, each x can only go to one y, but multiple x's could go to the same y. To be one-to-one, each x goes to a different y. So the x's are not repeated and the y's are not repeated. That allows us to solve equations using this property. So notice the base on the right is 2. Could we write 16 as base 2? Sure, it is 2 to the 4th. Now, since it's one-to-one, since the bases are the same, then the exponents have to be the same. And you can see that x would be 2. Let's try another one. Let's solve this equation. Notice the base is 1/3. Could we write 81 with the base of 1/3? Well, it's reciprocal. I mean, it was 81, now we have a fraction, so that means the exponent will be negative. And then 3 to what power is 81? Well, 3 to the 4th is 81, so 1/3 to the negative 4 will be 81. The negative reciprocals the base, and then 3 to the 4th is 81. Since the bases are the same, the exponents have to be the same, and x is negative 1/4. Now there's a special exponential function, a special base. It's called the natural base. The natural base is e, and it's about 2.718281828, but it's not repeating. It goes on to other decimals. And it's kind of like pi, so it doesn't repeat and it goes on forever, which means it's irrational. So it gives us, we use that an exponential function with that, it's just e to the x. The fun thing is if I pick any point on my function, e to the x, such as right there at 1, so the y value of my function is e to the 1, which is just e. Turns out the slope of the tangent line is also e to the x, or in this case it'd be e to the 1. Also turns out that this area between the graph and the x-axis, the area is also e to the x, or in this case e to the 1, since I'm going it to 1. That makes it very useful for calculus. So that's why we have the natural base. There are some applications involving exponential functions. First one that we're going to look at is compound interest. That's the formula for it, where A is the current amount and P is the principal, which is the initial amount. So this is money. So we're talking about money. So we put money into an account or borrow money from an account. R is the yearly interest rate, otherwise known as APR, annual percentage rate, as a decimal. N is the number of compoundings per year. Now, interest is compounded when it is calculated and added to your account. For example, if you have a savings account, it is compounded monthly. At the end of the month, they look at the amount of money you have in your account, they give you the interest for it, and that gets added into your account. Then the next month you have slightly more money, so you get slightly more interest. If you have a credit card, it's compounded daily. And T is the time in years. Well, the reason why the credit card is compounded daily is because it gives more money. Even if the interest rates are the same, which they're not, borrowing money gives you a much higher interest rate than putting in money. But if they were the same interest rate, the more compoundings per year gives you more money. So a daily compounding gives slightly more money than the monthly that they pay on savings accounts. So what if instead of just daily we went to be minutely or hourly or secondly, or so we let n become very large? Well, when n gets very large, we get e. E is 1 plus 1 over n to the n when n approaches infinity. So if we compound continuously or all the time, a would equal p e to the rt. And that's the maximum amount you could have in your account with compound interest.